how are the three sides of a right triangle related? Well, when I look at these three sides, I can use the Pythagoras theorem to relate these three sides together. So since the Pythagoras theorem relates the three sides of any right triangle, there must be some sort of relationship between the three sides of the right triangle that we use for trig. So let's take a look at this a little bit closer. So first of all, let's take a look here at two different triangles with the same ratio. So this ratio is opposite side of B to hypotenuse is 7 to 10. Here the opposite side to B, the ratio is 0.7 to 1. And in fact, the angle, although the sides of these triangles are different, does the trig ratio depend on the size of the triangle? And clearly the answer is no, because the trig ratio here, the cosine value of angle A is going to be adjacent over hypotenuse, or 0.7. I'm going to use 3 decimals here. And for sine of A, it's going to be, well, I can use a Pythagoras theorem here. So A squared minus B squared, sorry, C squared minus A squared equals to B squared. So we end up with 10 squared minus 7 squared is equal to, actually we'll call that A squared. So then A is equal to the square root of 100 minus 49 is 51. So square root 51. So then the sine ratio becomes root 51 over 10. And as a decimal value, just work that out, root 51 divided by 10 works out to be 0.7141, so I'm just going to round that to 4. And if I do the arc cos on my calculator, so arc cos of 7 divided by 10, and that gives me an angle of about 45.57 degrees. Okay, so this angle here is about 45.57 degrees, and that works out to be right. That's 7. That's a little bit longer than 7 because this angle is a little bit bigger than this one here. If I do the same thing here, I'm going to use arc cos of 0.7, so cosine is 0.7 to 1, or 0.700. If I do the arc cos, I get the exact same angle, and although this triangle here is much smaller than this original triangle, all the ratios are going to be the same. I can still use Pythagoras here, so 1 squared minus 0.7 squared is equal to A squared. So A is equal to 1 squared minus 0.7 squared is going to give me, 1 squared minus 0.7 squared is going to give me 0.51. Okay, so this is going to give me square root of 0.51. So square root of 0.51 divided by 1 on my calculator, it's going to give me the exact same value of 0.714. Okay, so regardless of the size, the ratios stay the same. Okay, it doesn't matter. The size does not affect the ratios of the triangle. So since that's the case, we should consider a triangle with hypotenuse of 1. Just to make it easier, that 1's a nice number. So when we have a hypotenuse of 1, what do the sine and cosine ratios look like? Well, if I have a hypotenuse of 1 here, this is A, B, and C. So if I were to look at sine theta, or sorry, sine alpha, it's going to be the opposite side A divided by 1, or in other words, it's just going to be the length A. If I do it for cosine, it's going to be adjacent over the hypotenuse is 1. Well, that's just going to give me B. Now, the nice thing about this is, if I use a hypotenuse 1 triangle, this length of A happens to be the same as the sine ratio A of sine of alpha. So this length and sine ratio actually are equivalent. And we can start treating the sine ratio as a length if the hypotenuse is 1. And that's very convenient because we can do math on lengths. a little bit harder to do math on ratios, although we can. It's going to be much easier to do math on some lengths. This length A and this length B. For the slope, it's just going to be the rise over run, so A over B. So there's my slope ratio, A over B, and that's the same as my tan ratio of alpha. Tan of alpha is going to be A over B. So why would we do that? Well, if I do that, instead of using a squared plus b squared equals 1 squared here, I can, instead of using a, since a is equivalent to sine, I'm going to rewrite this using the sine. So I'm going to say sine alpha squared plus b. Well, instead of using b, I'm going to use cosine alpha. So I can just say cosine alpha squared. And instead of equal to c squared, well, c squared, if I'm using this triangle, my c squared is equal to 1. And I end up with something called the Pythagorean identity. And notice, and the other part of this is, just understand that this, even if I change the angle of this relationship still holds. This length is still going to be sine, this length is still going to be b or cosine, and the hypotenuse is still going to be 1, no matter even if I drew a steeper triangle like this. So this Pythagorean relationship holds true for every single angle. So this is what we call an identity, because this works for every single right triangle. Sine of the angle squared plus cosine of the angle squared. Okay, so this length plus this length is always going to be equal to 1. And I can test this. Okay, and I encourage you to try this out on your own. If I just randomly choose an angle, let's say 13 degrees. If I do sine of 13 degrees, and I square it, and I add that to the cosine of 13 degrees, and square it, okay, I'm always going to end up with 1. I can choose any angle, and it will always equal 1. This is a nice, useful relationship, and it's called the Pythagorean relationship for trig.